Hello, my name is David Shriver, and today I'm going to be presenting our tool, DNNV, a framework for deep neural network verification. Deep neural networks are increasingly being applied in safety-critical domains, such as autonomous vehicles. To ensure the safety of such systems, it's essential that we are able to check that they conform to a given safety specification. To address this need, researchers have been exploring algorithms for verifying that the behavior of a trained DNN meets some correctness property. A DNN verifier takes in a DNN model and a property specification and outputs whether the property holds or is violated. In the past few years, many DNN verification algorithms have been introduced, and this number continues to grow. Unfortunately, several challenges remain that make verifying real-world networks difficult. First, verifier developers must keep up with the ever-changing ecosystem of neural network operations and architectures. While the space of DNN operators is quite large, DNN verifiers tend to support only a small subset of this space. Second, DNN verifier users carry the burden of rewriting property specifications and transforming their models to match a chosen verifier's supported input format. That burden is compounded by the diversity of input formats required by each verifier, as shown here. There's little overlap between input formats for verifiers, and even when using the same format, as in the case of the popular ONNX format, we find that the underlying operations supported can be different. This makes it difficult and costly to run multiple verifiers on a given problem, since the user must understand the requirements of each verifier and translate inputs to their formats. These challenges place burdens on developers, users, and the research community. To address these issues, we introduced DNNV, a framework for deep neural network verification. DNNV introduces a standard for network and property specification formats to help create more reusable benchmarks, and it increases the applicability of verifiers by performing property reduction and network simplification to formulate equivalent verification problems in a form supported by a given verifier. DNNV takes as input a network in the common ONNX model format, a property written in an expressive domain-specific language, DNNP, and the name of a target verifier. Using the utilities provided by the framework and plugins for the target verifier, DNNV transforms the problem by simplifying the network and reducing the property to enable the application of verifiers that would otherwise be unable to run. DNNV then translates the network and property to the input format of the desired verifier, runs that verifier on the transformed problem, and returns the results in a standardized format. DNNV introduces a standard for DNN verification input formats to aid the community in creating and running verification benchmarks. For networks, we chose the Open Neural Network Exchange, or ONNX format. DNNV currently supports a subset of the ONNX specification that is sufficient for existing verification benchmarks, as well as many real-world networks such as VGG16 and ResNet34. Due to the lack of a standard format for specifying DNN properties, we developed a Python embedded DSL for DNN properties, which we call DNNP. Embedding DNNP in Python allows for the rich ecosystem of the host language to be used in writing specifications. We demonstrate DNNP with an example of a local robustness property shown here. The property specifies that for all inputs x that are in the input space and within a hyperrectangle of radius e centered at the given input x0, the network should predict the same maximum class for both x and x0. In addition to the standard input format, DNNV also increases the applicability of verifiers by simplifying DNN models and reducing properties to more commonly supported forms. See our full talk for more details. We've implemented DNNV in Python with support for 13 existing verifiers. DNNV can be run from the command line by providing a property specification, network, and verifier. As an example, we will use DNNV to verify the local robustness property explained earlier for a fashion MNIST model with batch normalization operations. DNNV takes as arguments the path to the DNNP property specification, the path to an ONNX model, any parameters for the property, and the name of a verifier to run. DNNV will output the property being checked, as well as the description of the model being verified. It will then simplify the model, reduce the property, run the desired verifier, and return the result. In this case, Verify was able to find a counterexample in less than 2 seconds, even though the DNN contains batch normalization operations, which Verify does not support off the shelf. DNNV was able to simplify the network to an equivalent model and find a counterexample to the property. We also analyzed 19 benchmarks from the DNN verification literature to determine whether they would be expressible in DNNP and ONNX and whether they would be supported by each verifier using DNNV. Of the 223 pairs of verifiers and benchmarks for which support may be possible, 166 of them are currently supported by DNNV, an increase of over 2.4 times the 68 pairs that were supported without DNNV. In this work, we introduced DNNV, a framework for deep neural network verification. DNNV introduces a standard for network and property specification formats to help create more reusable benchmarks, and it increases the applicability of verifiers by performing property reduction and network simplification to formulate equivalent verification problems in a form that's supported by a given verifier. To learn more, check out our full talk or see our paper for more details. The DNNV tool is publicly available for download and reuse at the link shown. Thank you.